Yeah, so I think the stream is set. Okay, great. So let's go back to what we were looking at last class. Quickly recollect that. So we first introduced like what is this wave function, right? So it is basically some function. It's usually a complex function, and it is a function of space and time. So imagine you're sitting in this room and then there is an electron. We basically specify its probability at different locations, right? So, and different times. So this is a function that is complex, meaning at every point in this room, I have a different complex number. So it's a function x, y, z, and t. Sometimes this is also written as x bar comma t. So when I write this, it is basically a vector that includes all the space coordinates. So x bar is a vector which is equal to x, y, z. Sometimes, you also see people writing it as r bar t, right? So many different notations are there. In our class, mostly we're going to be concerned with one-dimensional wave functions. So we're going to usually write it like that, right? What do I mean by one-dimensional wave function? I mean that in the other direction, there's not much, there's no variation basically, right? So for example, if I have a string, then it's only changing along the x, right? So that is why if it depends on the symmetry of my problem. So if I'm considering a problem that is, let us say I'm considering a very thin wire and I want to know the wave function, I can usually approximate it by a single dimensional wave function, right? Now, if I'm doing talking about a quantum dot, which is a three-dimensional object, then you'll have to give all three dimensions, for example. So I hope you see that. So my wave function is a complex function that is a function of x, y, z, and t. And anytime you visualize this, I usually like to visualize it in terms of, there's a pond and there's a water wave in the pond, right? So it's exactly like that only. If the so imagine like a wave. Imagine there is a water and then there is a water wave. Imagine your electron like that, right? In three dimension, you can imagine it as like a stretcher. Once you visualize it in two dimension, imagine something like that in three dimension, right? In my mind, always I visualize electron like that, as if there's some water, there's some disturbance, and it's like propagating, right? So you can imagine it like that. Okay. Yeah. So, and we know that if I do psi conjugate multiplied by psi, and if I integrate it over all volume, so integrate over volume, this should give me 1 if psi is a wave function of a single particle. Because a single particle, there's only, if we go through the room and eventually we're going to discover at max only one particle, right? So the wave function has to normalize, wave function of a single particle has to normalize to 1, right? Okay. We discovered this, right? In addition to that, we are now, we also discussed something very important. When I write it like this, psi x, y, z, and t, this doesn't look like a wave, right? It's some arbitrary function of psi. Wave functions are not really arbitrary functions of x, y. They have wave-like characteristics. What I mean by that is, if you were to plot this psi, it would look like a wave. Okay, it would look like some kind of a wave, basically, meaning that it would go up and down in space. If you freeze the wave function at any given time and look at different locations in space, there is some places where it is 0, some places where it is high, and so on, right? And wherever it is high, that place keeps moving, right? So That is why we call it a wave function. It's not a general function. It's a function which has wave-like characteristics. Okay. And if we sit at any particular position in the room, and if I plot this psi, here I'm plotting mod of psi squared, right? If I plot mod psi squared, the amplitude of this complex function, if I plot it as a function of time at any given location, then also it'll have wave-like behavior, right? So it'll go up and down, it'll oscillate basically, right? So oscillation, this is the key feature of any wave-like mathematical object. It has to oscillate. How much does it oscillate in time dictates its frequency. How much it oscillates in space dictates its wavelength or wave number. Okay, so you see that, right? So there is a correspondence in a way between space and momentum, time and energy. Time and frequency, momentum and wavelength. Energy and frequency, momentum and wavelength. Okay. Fine. So this is my wave function. So it's not, I mean, not just an arbitrary, right? It is some function like this. Now in there also, remember I told you, we started talking about frequency and wavelength and so on. And I told you that we can define a wavelength exactly, right? Only if it is a pure sinusoidal kind of a function, right? Only for a pure sinusoidal function. This could be a function of space or distance, so space or time. If it is minus infinity to infinity in time, then we can, and it's a pure sine wave, then we can assign it a frequency. If it is a pure sine wave in space, we can assign it a wavelength. If it is, right, so this is basically infinitely extended sine waves. Now, these are not the only possible wave functions, right? These are some kind of wave functions. I could have some other kind of wave functions also that are not pure sinusoids. These are the kind of functions that are compact. What I mean by compact is that they don't extend to infinity. They kind of asymptotically approach zero as we go to infinity. So these are your full waves. These are actually wave packets. And when we deal with quantum mechanics and wave functions, generally we are only dealing with these two kind of waves, these two kind of functions, right? When I write psi, it's really just these two kind of these two kind of wave functions are the ones that are really relevant. Because if you look at the psi xyz t, it looks like a very complicated three-dimensional function of space and one dimensions in time. It could be anything, right? No, not really. They're basically just wave functions like this. Either they are infinitely extended, or they have a finite, or they have compact supports. Now within this region, we have three behaviors, right? Something that is very delocalized. This is infinitely delocalized. This is fully delocalized, meaning it has no location basically, right? It's fully delocalized. This is partially delocalized, or you can even say it's partially localized. And the other extreme, so from one end partially delocalized, and to the other end, which is fully localized, we have all kinds of possible wave functions in the middle, right? And I'm drawing here wiggles. You might be asking, well, is this in space or time? It could be in either one of them. So I could have a wave function that is, I have different combinations, right? I could have a wave function that is localized in time, but delocalized in space, right? Or I could have a function that is localized in space, delocalized in space and time. And we will look at those kind of functions right now in a moment, actually. From that is what we derive, the Schrodinger's equation, right? So I hope you can see the combinations, right? So I can have many combinations. I can have something that is delocalized in time and space. What does that mean? That means it's existed forever. It's going to exist forever. It's existed everywhere. It's existing everywhere and existed forever. right? Like that. Or you can think of something, events or quantum objects that are just localized in time and localized in space, right? That's also possible. Imagine a wave packet that is traveling. So that would be something that is localized in space and localized in time. Whenever we think of an object that we see in our daily lives, those kind of objects are localized in space and localized in time, right? So if I stand at one position, yes, it will come and go, right? It will not exist forever. Okay. And if you go to an ocean, for example, if you see a very large wave, those are examples of something that exists forever, spans for exists everywhere and exists forever. Okay. So all kinds of possibilities are there. So I'll write this scale here. So localized, delocalized. You may be wondering, okay, this is fine, but how is this practically relevant? And I'll show you how this is practically relevant, right? So I can say I have localized and I have delocalized. This is in space, this is in time. I can have all four possible combinations. Localized in space and time is actually a wave packet that is just traveling, right? Localized in space but delocalized in time, that is a frozen wave packet, doesn't move anywhere, right? Frozen wave packet is just standing there. Delocalized in space but localized in time, that is basically a wave that comes into existence then goes away, right? What is delocalized in space and time? That is like, imagine a big ocean, waves are keeping on coming, never stops, and you know that yes, forever it's been there, right? So things like that. So I hope you can now imagine, whenever you look at these kind of wave functions, should not scare us, right? It's just simply, these are the only possibilities. Okay. Yeah, when we go to two particle wave functions and so on, they're slightly more complicated, but not really that much, right? In fact, if I imagine a wave function as function of space, I can almost think of it as a vector. It's actually an infinite dimensional vector. And why is it so? Let me clarify that. So imagine having a scale, on minus infinity to infinity. Now at every point, my wave function will have some value, right? So imagine this. So how would I mathematically specify this wave function? I'd basically list a lot of numbers. In fact, I'd have to list an infinite number of numbers. So it is like a vector only in a way, right? So, so even your wave function, if it's a single dimensional one, it's easy to see that it's a vector. Even multiple dimensional wave functions, they're also in a way vectors only, but they're all vectors in an infinite dimensional space. So the world we live in is a three-dimensional space, right? Like that, imagine an infinite dimensional space and imagine a vector in that infinite dimensional space. You may be wondering, okay, why am I boring you with this? Not really. Those infinite dimensional vector spaces are actually called Hilbert spaces. So if you open a book on quantum mechanics, you'll see Hilbert spaces immediately, right? So those are Hilbert spaces. So when we talk about infinite dimensional vector space, and what are the vectors in that infinite dimensional vector space? Those are your wave functions, right? And operators are nothing but matrices in that vector. They're basically nothing but rotations in the in Hilbert space. So I'll come to that later, not to confuse you or anything, but I hope you see the analogy of wave functions. What are typical wave functions? They're looking like this. Either they're delocalized and delocalized like this in time and space, and they can be thought of as vectors also. Another thing I want to remind you is that only when I have a fully delocalized, it goes from minus infinity to a pure sinusoid, then only I can specify an exact value of frequency or wavelength. Okay, this is very, very important. Only such a delocalized wave function has a definable wavelength. So what does that really mean? Only if my wave function is fully delocalized in space, which means it extends. I'm drawing here, but it's actually uniform, right? So only if it extends in space from minus infinity to infinity, this is space, does it have a uniquely defined wavelength? And only if it has a uniquely defined wavelength, does it have a uniquely defined momentum? Remember, momentum is h bar k. K is 2 pi by lambda. H bar into 2 pi. Momentum is h by lambda also, right? So only when I have a uniquely defined wavelength can I have a uniquely defined linear momentum. What does that mean? That means if you ask me, okay, this is my wave function, what is its momentum? I'll immediately tell you, unless and until your wave function is infinitely delocalized, it's completely delocalized in space, don't even ask me what its momentum is, because it doesn't have a unique momentum. So if you tell me, yes, I have this wave function, it has this particular momentum, then immediately I'll know that it is infinitely delocalized in space. Okay. This is very important concept that many people don't get it. On a similar way, only if I have an in terms of time, only if my wave function had existed for from minus infinity to plus infinity, can I define a frequency, a unique frequency. And only if I can define a unique frequency can I define a unique energy, right? Because energy of the wave of the particle is h bar omega. Energy of my wavy particle is h bar omega. So now immediately you know that any particle that is that doesn't have an infinite lifetime doesn't have a fixed energy. Okay, so if you tell me this particle has a fixed energy of this many joules, immediately I know that it must have existed for all time. It must continue to exist for all time. So fully, it has no lifetime. It has infinite lifetime. Only then it has a fixed energy. Okay. This concept is extremely important, right? Nobody clearly understands this, but this is very, very important. Now, if I have a wave function psi, and if you ask me, okay, what is the energy of this wave function? Yes, I mean, I can give it an energy. If I give it a definite energy, instantly you know that it's delocalized in time. If I give it a definite momentum, instantly you know that it has a it's delocalized in space, right? Any wave function that has a definite energy is called an energy eigenstate. It's called an energy eigenstate. Okay. Now you might have heard this term, but I hope it's clear now. Any wave function that has a definite energy, only those kind of things are called energy eigenstates. Okay. Any wave function that has a definite momentum are called momentum eigenstates. Momentum eigenstates. Any wave function that has a definite position are called position eigenstates. Now we know very clearly that any wave function cannot simultaneously be a position eigenstate and a momentum eigenstate. Why? Because if it has a definite momentum, it cannot have a definite position, right? Because of quantum uncertainty. So either I have my wave function is a position eigenstate or it's a momentum eigenstate. Cannot be both. It can, however, be a momentum eigenstate and an energy eigenstate. That is possible, right? And I'll show you later where that is possible, but this is entirely possible that a wave function is both a momentum eigenstate and an energy eigenstate. That is entirely possible, but it cannot be a position eigenstate and a momentum eigenstate. Now, next question to you is, can I have a wave function? This is something for you, I think the answer. Can I have a wave function that is a position eigenstate as well as an energy eigenstate? Right? Turns out that it's not possible. I leave you to think of that as to why that is the case. Okay, so I hope this concept is clear of an eigenstate, why we call it as an eigenstate. The reason for that will come slightly later. This is anybody who has done linear algebra might recognize this word eigen, right? So it's an eigenvalue, eigenvector. So you might be saying, why am I using this word eigenstate? And there is a very good reason for it. The reason is that it comes back to this Hilbert space, right? So I'll come back to that slightly later once I introduce these things to you, right? So, okay, so I hope everybody understands the concept of a wave function, delocalization, localization, definite energy, definite momentum, and what is a eigenstate, momentum eigenstate, energy eigenstate, position eigenstate. I'll give you an example. So if I have a wave function psi that is e to the power j omega t minus k into x, right? This wave function, if you can see it, it exists for all values of x, right? All values of x, it exists. All values of time also it exists. So this is some wave function that is basically delocalized in time and space. In fact, it is called a plane wave function, right? Similar to like electromagnetic plane wave, right? So these are called plane waves. These are called plane waves. So this is a plane wave function. Now let us look at it. This clearly it has a frequency, right? And clearly it has a k number. K is nothing but momentum. So this wave function clearly has a unique value of momentum, and it has a unique value of total energy. So this is clearly an energy eigenstate. It's also a momentum eigenstate. Does it have a position? It doesn't have a position. Why? Because every value of x you put in, it will give you proper values, right? So, and looking at this function, I cannot say, can I really assign a unique value of x to this? No, not really, right? So it is not a position eigenstate. It's not a position eigenstate. So this is an answer. This is an example of a state that does not have a position eigenstate. It's not a position eigenstate, but it is an energy eigenstate, and it's a momentum eigenstate. Okay. Now I can give you another example of a wave function. I'll give you an example of a wave function that is a let's say a Gaussian wave function, right? So if I take e to the power j, x squared by 2, some number, something like this, x squared by 2 sigma, for example, and minus j omega t, right? So basically it's a Gaussian. Yes.
In this equation, here x, we can say here this is not a position eigenstate, but here x is also, we can put anything in x like omega and
first of all, कौन सा wave function का बोल रहे हो आप? इसका बोल रहे हो?
Yeah.
Plane wave का बोल रहे हो?
हाँ, yeah, for plane wave.
ठीक है, हाँ, right. So yeah, exactly, right. See, I'll come back to this thing later. Yeah, in this plane wave, yeah, you can put any value, right? You can put any value of x. And looking at this equation, is there any special constant, distance constant that enters into these equations?
No.
Exactly. That is why it is not a position eigenstate. Right? Any eigenstate, if I say it's an energy eigenstate, that means I can associate some scalar value with that. Right? I can associate a scalar energy with that. For this particular wave function, h bar omega is the scalar, energy scalar. Is that clear?
Yes, sir. Yes, sir.
Okay.
Thank you.
Yeah. Right. So and the same thing with k, right? I can do h bar k, and I say that's a momentum, and that's a scalar value. So this function clearly is a position eigenstate and a moment. It's an energy eigenstate and a momentum eigenstate, but not a position eigenstate. Okay, because there's no definite position associated with it. Okay. Right, and let me go on to the Gaussian wave function that I was talking about, Ej x squared by 2 sigma e to the power j omega t. Right, so I'm doing proportionality here, okay, because some of these cannot be normalized, right? They're not normalizable. So I'm doing proportionality. Okay, so this wave function, it is infinitely delocalized in time, but it is localized in space. Okay, it is localized in space, and but yet this is a very strange wave function because it is an energy eigenstate for sure. Why is it an energy eigenstate for sure? Because we have a constant, this omega, right? Its energy is h bar omega. It's an energy eigenstate. But this wave function is neither a position eigenstate. Why is it not a position eigenstate? Because I don't see any distance related constant appearing in the equation. Not this sigma, right? I don't have a constant, some constant distance, for example. So this is not a position eigenstate. Neither is it a momentum eigenstate. No. Right? So I can have things like this. Can I have a situation where I don't have a position eigenstate, nor a momentum eigenstate, nor energy eigenstate? Right? Think about it. What if I look at a particle in an electric field, right? Something like that. Okay, I'm not going to answer it. Some puzzle for you to think about. Can I think of a situation where I don't have any eigenstate? Okay, great. So this is a Gaussian wave packet. It is neither a position eigenstate nor a momentum eigenstate, but it is an energy eigenstate. Okay. I hope the ideas of what is an eigenstate is clear to you. Now let us go and derive the Schrodinger's equation. Right? You're all ready to derive the Schrodinger's equation now. And let us do that. So for deriving the Schrodinger's, well, it's not technically a derivation per se. It is more like, we will take some particular wave function and we try to see what equation it will satisfy. And we find that the equation it satisfies is a Schrodinger's equation. And so it's not really a derivation of such, but it's an instructive exercise. Let me just say that. And the wave function we're going to consider, excuse me here. Wave function we're going to consider. Sorry about that. These are my domestic difficulties here. Yes. So we take a wave function and let us consider a plane wave function, e to the power j omega t minus k into x. Where does this come from, right? So, I mean, this looks mathematically different. Where it actually comes from, imagine this kind of a function, right? Sine omega t minus x. So what is this? This is just a sine wave. And its frequency is omega by 2 pi. Its wave length is 2 pi k is 2 pi by lambda. It's 2 pi by k actually. 2 pi by k. That's it, right? So from there we say, okay, I take this complex number like this. And if I take the real part of that, then it looks like this, right? So that's where this comes in. But what is the probability of finding this particle at any point, right? So if you square it, you'll see that mod of psi will come to constant, right? It's independent of x and t. So if I consider a room like this, what kind of wave function is this? This is a fully delocalized wave function. It has a definite frequency, definite momentum, has no definite position. its probability of locating anywhere in this box at any instant is same. What is it? It depends on a normalization, right? So I'm not putting the normalization. That's why I'm saying proportional to, right? So let us take this kind of a function. In fact, you can say, you can call it, into A into something. You can do that also. And let us now establish what wave function, what equation, what differential equation. It is a differential equation because these are functions of x and time, right? Any function, what kind of equations do functions satisfy? It satisfy differential equations. So this wave function must satisfy some differential equation. We're going to try to find out what that is. And when we do that, we'll see that it satisfies Schrodinger's equation. Okay, great. So I take psi, it is a to the power j omega t minus k into x. And I'm going to simply first differentiate it. I'm going to take a partial derivative of that with respect to x. And I get a into e to the power j omega t minus k into x into derivative of this particular term with respect to x, right? So that would be minus j into k into x. Then I'm going to take the derivative of this with respect to time. Then I get a into e to the power j omega t minus k into x into j omega. Nobody pointed this out. There's no x here. Okay, so it's j into k, right? Like this. Okay. Okay, I hope any questions on this? Not really, right? I'm just doing differentiation. E to the power j x derivative, e to the power x differentiation is nothing but e to the x into 1. E to the power k into x, e to the power kx, derivative of this is e to the power kx into k, right? So e to the power j into kx, derivative is j into kx into j times x. And I'm doing partial derivatives. So okay, so okay, I'm sure you know this, right? So yeah. So let me write it again. I'm going to simplify this. So d phi by dx turns out to be equal to, I'm going to replace this by psi itself, right? So it is psi times minus j into k. Or I can write it as h bar into d psi by dx is equal to minus j h bar k into psi. Or h bar by minus j d by dx of psi is equal to minus j, yeah, is equal to h bar k into psi. Or I can write this as minus I times j and I, physics people prefer the I, okay? So don't confuse the two. Sometimes, you see I, j, the same thing. Minus I h bar d by dx of psi is equal to p times psi. Okay. Right. So immediately, this is where we say that IHD by dx is nothing but the operator and so on, right? So let me talk to you about what is this operator notation and so on. So what has actually happened is I have applied some operator on my function, and what did I get? I got the same function back multiplied by some scalar. Okay, that's what I got. So this is the operator. Because I operated with this particular operator, I got momentum times psi. That means this particular operator must be the momentum operator. Must be the momentum operator. Okay. Now let me tell you why, we go Hilbert space operators, why quantum mechanics talks about all these mathematical ideas. Very simple, right? Forget all this operator business for now. Let us go into our three-dimensional space. Imagine there is a vector here. Okay, if you rotate this vector, what will happen? If I rotate this vector, its length will remain the same sometimes, right? These are the kind of rotations sometimes. There are some other kind of operators. What they will do is, those kind of operations, they will not change the direction of the vector, but they'll simply change its length. Okay. So in three-dimensional space, any vector is notated by a three-dimensional vector, right? 3D vector. Basically denotes what is the projection on the little x hat. So any vector, let me give an example. Any vector in three-dimensional space, I'll give you one example, 2x hat plus 3y hat plus 5z hat, for example, right? This is a vector in three-dimensional space. I'm going to divide this by root of 2 square plus 3 square plus 5 square. So this is some unit vector in the three-dimensional space, right? And it's going to be represented by whatever this number is, 2 square plus 3 square, 2 by 2 square, this coefficient, right? I'll have coefficient of x, coefficient of y, coefficient of z. This is how we denote a unit vector in three-dimensional space, right? What is the operation that takes a vector in three-dimensional space, converts it into some other vector, right? And I put it to you that such an operation is basically matrix multiplication. So if I take a 3 by 3 matrix of some kind and I multiply by ax, ay, az, this is 3 by 1. This is 3 by 3, 3 by 1 should give me answer as 3 by 1. So anytime I take a three-dimensional vector multiplied by a matrix, 3 by 3 cross 3 matrix, I end up with another vector. So rotations and transformations of vectors must be a matrix multiplication. If matrix multiplication is nothing but transformation of one vector into another vector. It's not just rotation. These need not simply be, they don't need to be length preserved. Okay. So I could have a longer vector, turn it into a short vector, all kinds of any general transformation from one vector to another vector is covered by matrix multiplication. Okay, any doubt with that? Not really, right? 3 by 3 matrix multiplies 3 by 1 vector, gives me 3 by 1 vector. No doubt about that, right? There are some matrices, let me call this some special matrix A. And for any given matrix A, there are rather some special vectors. Okay, matrix is not special. Any matrix. There are some special vectors. If you multiply A for any matrix, okay, matrix is not special. For any given matrix, there are some special vectors. You multiply by that, A into x, you're going to get x multiplied by some scalar factor. Right. So given any transformation matrix, I can find some particular vector that it will, if I apply this transformation, it will give me the vector in the same direction, just length is scaled. Okay. These kind of special vectors are called eigenvectors. And for example, a 3 by 3 matrix will have 3 eigenvectors like that, right? It'll have a fixed number of eigenvectors. And they'll be unique. So I give you a matrix. Well, all 3 need not be unique, but it'll have total of 3 eigenvectors, right? Sometimes there are degenerate eigenvectors. Those kind of things also are there. So let's not go too deep into the linear algebra theory, but I hope I'm revising some of your concepts, right? So I'll have some vectors, given any matrix, I'll have some particular vector that will, if I multiply A into x, I'm going to get So A into X, I'm going to call this special ones, right? I'm going to give it a name X into I. Okay, that means it's not just any vector, right? It's only for the specific eigenvector. That will result in some constant Ci multiplied by X into I. Right? So this is my original matrix. This is my eigenvector. This is also my eigenvector. This is my eigenvalue. Eigenvalue. Okay. Any doubt about this? I hope it's clear, right? Any questions about this? Anybody? Any questions about this? No, right? So I hope this is clear, right? Yeah. So basically linear algebra, right? Nothing surprising. If you want to visualize it geometrically, what it basically says is this: you give me any matrix. And first I told you that any matrix, any 3 by 3 matrix, will take a vector and transform it into some other vector in 3-dimensional space. No doubt about that. For a given matrix, I can always find some unique vectors called eigenvectors that have this special property. A into X of A into eigenvector is some eigenvalue times the eigenvector. Great. Okay. Now notice the similarity between this and this. Okay. Now do you see why we have eigen states and so on, all these ideas? That's where this comes in. So to be very clear, so I took Ax equal to Bx, and basically these eigenvectors, what are they? They're basically solutions to these kind of problems. Ax is equal to Bx. If you solve this equation, then you get the solution to these equations are basically eigenvectors, right? That's what they are. Great. So similarly, I just saw that minus I h bar d by dx multiplied by my wave function was giving me rho times the wave function. You notice the similarity between this, right? In addition, I already told you that X is a vector, right? But I also already told you something else, that this psi, this is also a vector, but it's an infinite dimensional vector. So what should you conclude? Immediately you should conclude that whatever this guy is, he must be a matrix. But he must be an infinite dimensional matrix. Infinity cross infinity is the size of that matrix, right? Now, you might be, why don't we just think about it in terms of derivatives? And why are you really hurting my brain by bringing in this matrix note? It doesn't even make, it's not very comfortable, right? Why are we talking about infinite matrices? Are you nuts? And so on, right? Not really. The reason is that once you notice the mathematical structure of any kind of quantum operation, we know that, right? So if I have any equation, any operator, it will have its eigen states. So if I have a momentum operator, I can say, okay, what are the eigen states of the momentum operator? And because these are infinite, remember 3 by 3 matrix has 3 eigen states. IH d by dx is an infinite dimensional operator, so it should have infinite eigen states, right? And that's it. So that's where the notation eigen state comes in. It's eigen wave function basically. It's called eigen state. Great. And this is obviously the eigenvalue, right? Right. Great. So that's good. So we got this. Next question you might be asking is, once again, you may not see the utility of why we are doing this, right? Why the hell are we connecting this to linear algebra? I mean, I can simply, this is differentiation, right? I can simply go on doing differentiation, but not really. The reason is that linear algebra, this is a linear algebra. There is lots of very interesting theorems in linear algebra, right? About Cayley-Hamilton theorem, lots of interesting mathematical structures and so on. Once we see the mathematical analogy of quantum mechanics and linear algebra, and anytime you open a quantum mechanics book, you might be seeing all these psi, operator, commutator, and so on. You might be thinking it looks very abstract, right? But not really. If you know linear algebra, and if you know the idea of these eigenvectors and infinite dimensional and so on, already you know the entirety of quantum mechanics, mathematics of quantum mechanics. At least this is it. Nothing more than this, right? So let us take this idea a little bit further. Any questions, please ask me. I hope this is not too confusing. Okay, you have to stretch your head a little bit, but that's all there is to it, right? So we have one equation. We know that IH d by dx is the momentum operator. Let's go find out other operators. If we next go with this particular, okay, I started with position one first, started with this guy, right? Next, let's go with this particular equation, see what it reveals to us. This guy, right? What does this reveal to us? So if I write it down, I hope I'm not I'm partial derivative of, I'll pull it down. Let me just copy this. It turns out to be equal to psi times j omega, right? D psi by dt is equal to psi j omega. So partial of wave function with time is j times omega times psi. This implies that h bar by j into d by dt, dou by dou t partial is equal to h bar omega times psi. Nothing but E times psi, right? So that's it. So what do we conclude? We conclude that this particular wave function, remember we started with this particular wave function, right? Clearly, it is an it is a eigenstate of the energy operator. Why? Because I'm doing something to psi, I'm getting E times, and immediately we conclude that this must be the energy operator. So minus I 1 by j becomes minus I h bar partial with respect to time must be the energy operator. I h bar dou by dou x must be the momentum operator. What is the time of, what is the position operator? How do we get the position, right? There's no simple notation for that. Definitely e to the power j omega t minus kx is not a position operator, right? So for now, we're going to simply call it the x. We just put a cap on that and call that as the position operator. Okay. There's no, I cannot split it in further. Okay, I can just simply call it as the x. So I can say that, okay, if I operate this psi, if psi is an eigenstate of, if psi is a position eigenstate, then I would have gotten some constant times psi. Okay, so if you can find a position eigenstate somewhere and operate on this, then you get this. But right now, because our plane wave, this guy is not a position operator, not a position eigenstate. I mean, I cannot find something like this, right? Okay, great. So I have momentum, I have energy. Now remember momentum, remember we had p square by 2m is kinetic energy, right? So I can now go ahead and do kinetic energy operator. What is a kinetic energy operator? It is nothing but p operator dotted with p conjugate by 2m. Same as I into h bar dou by dou x dotted with minus I h bar dou by dou x by 2m. So I and I gives me minus, minus and minus 1 cancels. So it is, hold on, I'm making some mistake here.
So then I square will be minus 1.
Yeah, no, I'm making a mistake because, yeah, what I'm making a mistake is this. This is where I made a mistake. It's basically like this, right? It's basically p square by 2m. So what I have to do is I have to do I h bar dou by dou x. This I have to square. Okay. So see, I have to apply this operator 2 times basically. I have to do I h bar d by dx. I have to apply this to this first. Then I have to once again apply I h bar d by dx. Right? That is how p not, it's not p dot with p conjugate. That was the mistake. So kinetic energy operator is simply going to be minus h bar squared by 2m. Minus h bar squared by 2m, dou squared by dou x squared. This is my kinetic energy operator. Now, anybody who has seen Schrodinger's equation immediately recognizes this operator, right? So if you know Schrodinger's equation, you know, oh, wow, this is where it is, right? So we are getting there. We must be getting there somehow, right? Okay, so this is my kinetic energy operator. How do I do the potential energy operator? What is my potential energy operator? Potential energy operator is going to be given by whatever is the potential as a function of x multiplied by psi. Because my psi, this plane wave function, is not, it's not a position eigenstate. It does not have a fixed potential energy. I cannot, it's not going to be a potential energy eigenstate also, right? Why not? Because see, potential energy is a matter of distance, right? So if I'm located at a particular height, then I say, okay, this is your potential energy. So if my wave function is not a position eigenstate, I should not expect it to be also an eigenstate. I should not expect it to also have a, I should not expect it to have a constant potential energy. Okay, great. So that's that. So potential energy is simply given by ux into psi. Great. So now we have all the tools needed to go ahead and see the Schrodinger's equation. What I'm going to say is kinetic energy of the particle plus its potential energy must be equal to its total energy. Now remember, in quantum mechanics, if I ask you what is its energy, right, you cannot simply say, oh yeah, its energy must be E. No, right? Anytime somebody asks you what is this particular quantity, what you have to do is take the particular operator, multiply that by the wave function. That's what you need to do. So, so this particular equation, which is the equation of conservation of energy, we're going to now express it in the language of operators. And that is what gives us the Schrodinger equation, right? Great. So let's do that. So minus h bar squared by 2 mass into d squared by dx squared of psi, which gives me the kinetic energy plus potential. I'm going to write it as u of x, okay? And the reason is when we do voltage, this equation is in volts, right? When I say V, that is measured in volts. Let me, maybe I'll take a side here. So let us say I have a positive charge here, okay? It is going to set up an electric field everywhere, right? And if there is another positive charge at infinity, if I have to bring this anywhere from infinity, anywhere else other than infinity, I'm going to have to pump in energy, right? So let us say the particle is here, then it has, over here its potential energy is going to be 0. Here it will have definitely slightly more potential energy. And if it is right at the charge, it's going to have infinite amount of potential energy. Potential energy is defined as the energy needed to literally bring it from there to here, okay, in the presence of an electric field. And its units is going to be in electron volts. So remember, potential energy, how do we calculate the potential energy in electric field? So you basically, whatever the electric field is there, and your charge is there. So you need to multiply the charge by the electric potential, right? So its units is in electron volts. So that is why in some books you have V of x. I always prefer U of x, because I always prefer U of x, because in my mind, I always have to keep in mind that this is the potential energy, right? And this is going to be a function of x and time. This wave function is going to be a function of x and time. Let me add that. Okay, we need to add that. So x and time plus u of x and time multiplied by psi of x and time. So when I do this, I must get the total energy, right? So I'm going to say this is equal to minus, what is the total energy operator? It is minus IH d by dt. Minus IH bar partial by partial t of psi x of t. What is this equation? This is your Schrodinger's equation. Schrodinger's equation. What we have established is that a plane wave function satisfies this particular equation. It turns out that if you don't have a, so if a plane wave function must satisfy this equation, Schrodinger made a leap. There is no proof. Okay, you cannot really prove it. What he made a leap is that, okay, until now we proved infinitely delocalized waves, right? Like pure sinusoid waves satisfy this particular equation. What he made a leap, he said, okay, let's say I have a wave packet also, something slightly more localized, that will also satisfy the same equation. That part we have not proved, right? That is an assertion. So that is why it's a Schrodinger's equation. It's not a Schrodinger's theorem. Not proved. What did we prove? We proved that if it's a sinusoidal wave function in space and time, then it will clearly satisfy Schrodinger's equation. That is what we have proved. Then Schrodinger did exactly this. And once he did this, what he said, okay, fine, if this is the case, then can I, what he proclaimed is that, okay, even if I have a wave function that is low, more confined, that is a compact wave, that will also satisfy this exact equation. Okay, now it becomes a matter of you apply a given potential, and you then find out what kind of wave functions will satisfy that particular potential distribution. Okay, and this is exactly what we're going to do in continuing classes, right? So it will become slightly more mathematical. We'll basically consider different kinds of potentials and see what kind of wave function satisfies those potentials. That is what we're going to do. But I hope you see where, I hope you also recognize now where this idea of operators comes in. This is it, right? Nothing more than this. Basically, they took this, first they said, okay, quantum particles behaves like waves. And then what is the simplest wave we know of? Plane wave. So they said, yeah, let's assume that a particle, that this fundamental particle is a plane wave, right? Then what equation will it satisfy? That's what they did. And they did, and then he discovered, he discovered this particular equation. And when they realized, that they were doing this IH, then they noticed the analogy between this and matrix. And so they said, okay, this is great, because now I can build an entire mathematical machinery on top of which is completely based on linear algebra, right? Where, I'll tell you where, because see, there are some properties that eigenvectors must satisfy. There are some properties that eigenvalues must satisfy, all very rigorously established by linear algebra. And that is why, okay, I think screen went off here. Rigorously established by linear algebra. Somebody is asking some question, I think. Should energy be what is it? What are you asking here?
Sir, it was about the sign only. I think with energy it will be plus iota h squared dou by dou t, like not negative, I guess.
No, it is no. It's minus IH only.
Okay,
because see, you can see the derivation here, right? So if I derive this with the time, J will come here, but then I'll have to take it to the other side. Okay, see, I get the equation d phi by dt is phi times j omega. Okay, agree with this?
Sir, your screen is not visible.
Uh, yeah, so if you just take this wave function, take the partial derivative with respect to time, I'm going to get d psi by dt, dou psi by dou t, partial psi partial t, is psi times j omega. Okay, this much is clear, right? So now if I take that, I have to, j will come down here, na?
Yes, sir. But in the then in the momentum operator case, the derivation of momentum operator, then
No,
it
momentum
should not
operator
be.
case is correct. No, I'll
No,
show
sir.
you.
Actually,
See, if
sir,
I do
here,
moment, because
yes,
यहाँ पे minus है ना यहाँ पे.
multiply both numerator and denominator by
This
j.
is j omega t, but here see it is minus jkx. So d psi by dx is minus jk psi.
Yes, sir. But here, if we will to take j operator in the numerator, we'll have to divide both numerator and denominator with j. Then the denominator
Hold
will
on.
be.
So hold on. I did h by minus j. Yeah, this is plus. You're right. Yeah, this will be
Sir,
plus.
but sir, actually momentum operator is minus iota h cut dou by dou x. So I think there is
No. It's no. It's no. You can see. It depends on how you define. I could have done j kx minus omega t.
okay, sir. Okay, yes, sir.
I could have done it that way also.
Yes, sir. Yes, sir.
Depends on how I take this, right? So
Yes,
the
sir, yes.
bottom line is both of those signs will be different.
Yes, sir. Yes, sir.
Okay. So this equation is correct. There is a minus in the Schrodinger's equation.
Yes, sir.
Okay. And time also is IH d by dt.
Yes.
Right. So what will happen is what will happen is that see my wave function has e to the power j omega t. Na? This could be plus or minus. So this, some people take e to the power plus j omega t, some people take e to the power minus j omega t. There this sign thing will cancel off. Okay. Yeah. Okay. So right. So this compact wave functions also satisfy Schrodinger's equation. Okay. Now I'm going to talk about certain wave functions now, which are eigenstates, right? So I have psi that are energy eigenstates and position eigenstates. Momentum eigenstates. What we found out is that we can have states that are both energy and momentum eigenstates, and those kind of wave functions are basically your plane wave wave functions, and they clearly satisfy Schrodinger's equation. You can also take, right, in some situations, like the Gaussian wave packet that we just saw, right? So you can go and check to see, if it satisfies Schrodinger's equation and so on, and there will be some constraints, right? Now the question is, what are the eigen values, right? What are the different energy eigenvectors and so on? That completely depends on this particular potential, right? So usually how we do it is, what is given to you when you solve a problem using wave functions, the potential is given, right? So always the potential is given, and wave function has to satisfy this equation. So we then go ahead and solve the equation and see what are the possible answers, what are the possible wave functions. So potential is a parameter. Wave function is really the answer. Given a potential function, that constrains what possible wave functions can exist. Okay. And mass and everything really not really that much of a parameter. Mass of the electron is fixed, right? At least the rest mass of an electron in vacuum, that much is fixed. When we go to crystals, we do effective mass and so on. I'll come to those later. Right now, we are only talking about one electron, which is in the universe somewhere, and we are imposing some kind of a potential function on that. So how do you impose potential, right? What are the ways in which you can impose a potential? Oh, again, my video is getting cut off. Just a minute here. Yeah. I think it's because of my, okay, it's a low battery thing. Right. And this is an aspect that people don't really talk about, and so I really wanted to talk to you about it, right? So how do we impose this potential? That potential has to be imposed by some other atoms. It is either, well, not necessarily, it can be either some light wave, it's either some light wave which has an electromagnetic field. That is one way in which this potential can be imposed. A second way in which this potential can be imposed is if you have other charged objects, right? So whatever imposes this potential is also a quantum field. It's also a quantum object, right? And the more complicated your potential is, internal dynamics of that, right? That quantum system might be even more complicated. So luckily, we are able to kind of partition the universe into part of the universe that imposes the potential, and consider the electron in isolation, right? So little bit of a philosophical thing. If it bothers you or if you don't get it so easily, don't worry about it. I just wanted to put it out there, right? Right, and nobody really completely understands it so well. This is still at the very edge of human knowledge, right? This is called quantum foundation theory, and this is very important right now in quantum computing and decoherence, because we have quantum noise, right? So how do we reduce that? How do we get thousands of qubits? That is where we need to thoroughly understand interaction of quantum systems, one quantum system and a larger quantum system. That is where that comes in, right? But in the initial days, people, they put everything else in the universe, be it another light wave or be it some other collection of atoms and electrons that creates a potential. They clubbed it all out into just a potential function. And they went ahead and solved this equation. And what is the test, right? This is the math. I will have to solve this. I'll have to impose different kind of potential, see what answers I get. I do experiments, and they did exactly that, right? So they did exactly that. Turns out every single answer they got correct, right? So that is why we know that that's how people keep using this formalism. But we have reached a stage where now humans need to wonder about this even deeper level, right? How quantum systems really interact with each other. Yeah, so going beyond one, Schrodinger's equation is mostly for single quantum objects, right? It works really well in almost all cases. The only case where it wouldn't work is, if your relativistic effects are coming in and so on. But otherwise, it works really well. The open question is why it works really well. How is it that we can club everything in the universe into this potential function? And why does it still work? Okay, there are many reasons for that, and people are, this is exactly what people are working on right now in foundations of quantum theory. Okay, so very, very fascinating stuff. A lot of open questions. Nobody really has a complete answer to this yet. Okay, fine. So let me see where we are on time. We are good on time. Let's proceed. Great. So that's fantastic. So let us take the Schrodinger's equation for a test drive. Right. So here's our equation: a square by dx square psi x comma t plus u x t psi x t equal to I h bar d by dt psi x t. Right. So let's take it for a drive. And what do I mean by take it for a drive? What we usually do is we play with it, right? We put some parameters, we put some simple functions, then see how this equation behaves. What kind of solutions will it give me? In order to do that, I'm going to introduce one more simplification here. And anytime you have a partial differential equation, right? This is a partial differential equation. And how do we solve a partial differential equation? The first trick is we don't solve it. Not solve it. This is the first way to solve a partial differential equation, is not solve it. What do I mean by that? I'm not being chippy here. What I mean by that is we want to convert it into an ordinary differential equation, first of all. Whenever possible, want to convert it into ordinary differential equation. Not solve the partial differential equation. How do we do that? Right? A very tried and true method, right? It's called the separation of variables. And what we do that is we're going to break it into something that is function only of distance, and another thing that is something that is a function only of energy, of time. So, and f of t, I guess, right? No problem. Something like that. So we say our wave function is separable. So this is the way to solve. This is a way to solve Schrodinger's equation. In fact, this is exactly what happens when you take a proper quantum mechanics class in physics or whatever. They're going to first try this way of solving things. Right? Let us see what happens. Right? Let us remember, we have to, in any equation, we guess a solution, see how it works out. Right? So let's do that. So minus h square by 2m dou square by dou x square. I'm going to substitute Vx f of t plus u of x t phi of x f of t equal to I h bar d by dt into phi of x f of t. Now, this is good because here I have a partial derivative only with respect to time. Here so let's simplify this. This is going to turn out to be like this. I can write this as f of t into minus h squared by 2m d squared dx squared phi of x plus u of x t f of t phi of x equal to I h bar partial of time f of t. Phi x comes outside. Now let's divide everywhere by phi x into f of t. After doing that, so basically this will get out, and here this will get out, here this will get out, this will get out. But what will happen is I'm going to have a f of t in this denominator here. I'm going to have a 1 by psi of x in this particular term here. Okay. Can I put this into two different equations? You can, only under one condition, right? Provided this guy is also separable. Your potential must also be separable. If that is not separable, then you are out of luck, right? But let's assume that it is separable. And in fact, what we'll do is we'll say that that does not have any dependence of time, right? We'll say it is completely time independent. It's a static potential. Okay, not changing at all. In that case, on the left-hand side of this equation, we have something that is only a function of space. And on the right-hand side, we have an equation that is only a function of time. Then we are saying both of them have to be equal at all possible values. So the only way in which that can happen is if both of these things are some constants, right? So that means this entire thing must be equal to this, right? And all of them must be some constant that does not depend on x or t, because it has to be true for all values of x and t. So this gives us two equations: minus h squared by 2m, dou square by dou x squared, plus u of x, phi of x is some constant, basically. And I'm going to call it E times psi of x. Right? I'm going to call this entire, whatever constant, this constant, I'm going to call it E actually instead of C. And it will turn out that this is actually, we know this operator, right? I'm taking the kinetic energy operator, potential energy operator, operating it on this wave function. And so I know that I should get a energy eigenstate, basically, right? I should get the total energy operator, basically. So making the assumption that under the assumption if the potential is not changing with time, we know that automatically the solution of Schrodinger's equation will be an energy eigenstate. That's what we have proved, right? Right. So that is my first equation. In fact, this equation is called a time-independent Schrodinger's equation. What about the second equation? No problem. If you solve the second equation, what will happen is you get the idea that f of t is e to the power j e by h bar into t. That's what you get. So it's a time dependence, basically, right? So second equation is not very interesting. The first equation is interesting. This is the so-called time-independent Schrodinger's equation. And automatically, even without doing anything, we have concluded that all such possible solutions must be energy eigenstates. Which means that they must always have constant energy. Their energies don't change, right? So the solutions to these Schrodinger's equation, they basically those wave functions are all energy eigenstates. So all the solutions of time-independent Schrodinger's equation, basically what that gives you, it gives you all possible energy eigenstates, and it will give you the eigenvalues also, right? So we are solving an equation of the form ax equal to b into x, right? When we solve this TISC, essentially we end up with final answers will be what are the energy eigenstates, what are the possible energy eigenvalues. That's it. Okay, now once we know this, now you can ask me, okay, what are the possible values of psi of x? Psi of x, well, okay, maybe before that I need to tell you this answer. So I hope this much is clear, right? Everybody is clear until this part. Let's see where we're doing. Okay, we're almost doing well on time. I really wanted to introduce this much here. Next, we're going to consider superpositions of states and things like that. And don't let that scare you at all, right? It's very simple. So we got this idea. Remember, if I have any differential equation, so if I have any differential equation, let us say consider the differential equation d by dx of f is equal to 3 times x, for example. So what is f? F is 3x squared by 2, right? Yeah, 3x squared by 2. right? So, this is one of the possible solutions, right? So now imagine, however, a different equation: d square by dx square of f is equal to 3 times f, for example. So this is, you can write it as d square f is 3 times f. So d square equal to 3, d is equal to plus or minus root 3. And so the possible solutions of f are constant a multiplied by e to the power minus root 3x plus b times e to the power plus root 3x, right? So we always express the solution as a linear combination of the eigensolutions. So same thing must happen here also. If my wave function satisfies this equation, this will give me certain energy eigenstates. So my final answer must be some linear combination of phi1x plus a2 into phi2x plus a3 into phi3x and so on. Okay, this is your superposition theorem. This is where the whole idea of quantum superposition, dead cat, alive cat, all these ideas come from this thing. Okay, and from a differential equation point of view, it is not surprising. The time-independent Schrodinger's equation happens to be a second order differential equation, right? It's a second order ordinary differential equation. And because phi is an infinite, this is an equation happening in an infinite dimensional Hilbert space, there are infinite number of eigenvalues. Either in some cases it will be countably infinite, in some cases it will be uncountably infinite, and in some cases it will be finite. Okay, all kinds of you will get finite eigenstates, infinite eigenstates, all different combinations arise depending on the nature of this potential function. Don't let this confuse you. When we see the special cases one by one, you'll automatically realize what I'm talking about. Right now, we are looking at it a slightly higher point of view, right? So in terms of operator notation, if you want to write Schrodinger's equation, basically we write it in the following way: H psi is equal to E psi. For the time-independent Schrodinger, where H is this is called the Hamiltonian. It's called the Hamiltonian. Hamiltonian is basically adding kinetic energy and potential energy. That's all, right? That's sum of kinetic energy and potential energy for a classical system used to be called it Hamiltonian. And that's why this operator, this particular operator is called the Hamiltonian operator. And this IHD, this is called the energy operator. They're different, okay? Hamiltonian operator is different from the energy operator. They're two different operators. Hamiltonian operator, as you can see, Hamiltonian operator will have a combination of two operators, right? And energy operator simply divides by time. So they're different operators. And Schrodinger's equation is basically, in terms of operator notation, it is a statement that H psi is equal to E psi. Hamiltonian operator of psi is equal to energy operator of psi. Right? So it's just a metaphysical way of looking at it. You'll see all these kind of things mentioned in quantum mechanics textbooks. But what I hope is that this is hopefully somewhat clear to you now as to where the Schrodinger's equation comes from. We start from wave function, and we know what they satisfy, right? You may not, unless you have solved it, you may not have an idea as to for any given potential what kind of wave functions are possible, how does the energy eigenvalues behave. Those kind of things is what we're going to look next. By specifying different values of ux. We specify different values of ux, solve the Schrodinger's equation, see what answers we get. Excuse me. Can I close? Any questions before I close?
Sir, I had one question.
Yeah, please.
So is it possible to have a particle or a wave function with zero energy, like zero kinetic energy and zero potential energy as well?
Okay. It's not possible, right? And the answer is actually very simple. If a particle has zero kinetic energy, what does that mean? It means it's not moving, right?
Yes, like zero momentum.
It means it's not moving. And so that is where you have a problem, right? Because it has to be, if it's not moving, then you have, definitely what its velocity is. Its velocity is zero, right? And if it's not moving, we know that it has to be at one particular position only, na?
Right.
So you have given me both its position and momentum to full certainty.
I see. Okay.
So it violates our uncertainty principle.
Uncertainty principle.
Exactly. Right. And that is why, that is precisely why we cannot have a stable particle. Even at 0 Kelvin, particle will never be found idle. And this is the reason why we have something called 0-point energy in quantum mechanics. Everything has energy even at Can you hear me? I think, Pankaj, are you still there?
Yes, I thought the meeting got cut off, so I just...
Sorry, I got cut off. Yeah, I think I answered your question, right? So that's pretty much it.
So like, sir, at 0 Kelvin, then what do we have? Like potential energy or kinetic? Because we say that atoms are not in motion anymore. Like, so...
No, that's not true, right? So,
Okay.
yeah. It will still have some energy even at 0 Kelvin as well.
Okay, I see. Got it.
Yeah. Okay. So that is why it's called 0-point energy.
Okay.
Okay. So yeah, there's no freezing. That this is at 0 Kelvin, things not moving at all is a completely classical concept. Not true at all. Not true at all. Okay.
Yes, sir.